Alright, so in this video we're going to review thermodynamics, so Hess's law, how to calculate heat of formation, and also talk about Gibbs free energy. Alright, so when we talk about kinetic energy, and temperature, at a higher temperature you're going to have more kinetic energy. So if we're looking at this chart right here, remember you're going to look at the peak because it's showing all of the molecules, the range of speeds that they could have here, but you're going to look at the peak. And if I look at O2 at 25 degrees Celsius and I compare it to 1,000, well, at 1,000 degrees Celsius the average speed is about 800 meters per second, and at 25 it's about 400. So anytime that we increase our temperature, we're going to increase our kinetic energy and we will increase the speed. But remember, temperature only affects kinetic energy. That's the only factor that will impact kinetic energy. So at 0 Kelvin, the kinetic energy would be 0, and that's called absolute zero, which we still have not actually reached that yet, but technically at that temperature, kinetic energy would be 0. Now if you have a particle diagram, if you have a higher temperature, you should have more kinetic energy, and you can show that by having the lines at a greater magnitude. So heat can be calculated with this equation. So little q is heat, and that's equal to the mass of something multiplied by specific heat multiplied by delta T. And we use this equation when we're dealing with heating up a substance or cooling it down. That is when that comes into play. Oh, and then also if Q is positive, then heat is added to the energy, or added to the object. If Q is negative, then heat was taken out of that object. So a 21.3 gram sample of metal is heated to 70 degrees Celsius and is dropped into 62.5 grams of water at 21 degrees Celsius. The final temperature of the water is 24. Given the specific heat capacity of water is 4.184 joules per gram degree Celsius, calculate the specific heat. Okay, so basically a piece of metal was heated up and then dropped into a cup of water, and they measured the temperature change of that water. We're trying to get the specific heat. So let's divide out all the information we have, because we have information about the metal and we also have information about the water. So for the metal, my mass is 21.3 grams. It's heated to 70 degrees Celsius and then at that point it was dropped into the water. So the water should heat up as the metal cools down. So its initial temperature is 70 degrees. Because it was heated up to that and then dropped into the water. Let's see what else was given to me. Well, the mass of the water was given, 62.4 grams. The initial temperature of the water was given, it's 21 degrees Celsius. And the final temperature of the water was 24, which means that the final temperature of the metal should also be 24, because they continue to exchange energy until they have hit the same temperature. All right, and then it also gives me the specific heat of the water. Calculate the specific heat of the metal. So I'm looking at for C of the metal. Well, I know that Q is equal to MCAP. And if I'm looking for C of the metal, I don't have enough information to solve for C of the metal yet, because I don't have Q. I have mass and delta T, but not Q. But remember, in this situation, heat energy is lost by the metal and then gained in the water. So the heat should actually be the same. It should be equal to whatever energy the water gained. Well, do I have enough information to solve for the Q of the water? Well, I have mass, I have delta T, I have C. I do have enough to solve for Q here. So that's what I'm going to do. I'm going to solve for Q of the water. And then I'm going to go back and solve for my specific heat. Delta T, remember it's final minus initial, so 24 minus 21, so 3. All right, so if I plug that in and solve, I'm going to get 783.24 joules. All right, so now that I have that, well, the heat energy gained by the water is equal to the heat energy lost by the metal. So here, Q is positive because the water gained it, but with the metal actually lost that energy, so it's going to be negative. So it's going to be negative 783.24. So now I'm going to plug all of this information into Q, or Q equals MCAT, and get C. All right, so my Q is negative because the metal lost that energy. And my mass is 21.3. C is unknown. And delta T should also be negative because my final is lower than my initial. So if I have a negative delta T, my Q should also be negative. All right, so if I plug everything in and solve for that, for C, I should get 0.799 joules per gram degree Celsius. Please, 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 if you're doing FRQs, do not forget your units. Do not forget your units on FRQs. All right, so the specific heat was 0.799. All right, so there might be maybe one question on the multiple choice maybe about work. So basically, if you have a gas and you're heating up that gas, those molecules start to move. Well, they start to move, they're colliding more with the container, and if they happen to be in a piston, they can actually do work on that piston and move the piston up. So if that happens, that energy is being transferred into work. So work can be calculated by taking the negative pressure and multiplying it by the change in the volume. So this would only really be applicable if it was a gas problem and maybe something in a piston. So basically they can look at the change in the volume, so how much did the volume change, so how much did the piston go up, and multiply that by the pressure to get the work done. Well, the reason that this is important is because if you're looking at the exchange of energy, some of that energy gets used as work. Well, change in energy is equal to the work plus the heat. So if we're heating something up, we're adding energy to it, that's Q, but some of that energy gets transferred into work. So remember, energy is always conserved. So the change in energy is going to be equal to the heat and the work. So if the gas expands, so if it's moving up, it's doing work on something. And if it contracts, work is being done on the gas. So basically, if it squeezes down, work is being done on that gas. All right, so heating and cooling curves. If we're looking at a heating curve, remember, anytime that you see a flat line, that's a phase change, because what ends up happening here is as I heat up a solid, when it gets to the melting point, all of that energy, instead of being used to change my temperature, goes into breaking those intermolecular forces. So my kinetic energy is constant here, which is why my temperature stays the same, because remember, temperature and kinetic energy are very much related. So anytime I have a flat line, that represents a phase change. So if I'm looking at this one right here, I have a solid at the lowest point, and I heat it up until I get to the point where it's at the melting point, and then all that energy that I'm adding is getting put into changing the phase, so breaking the intermolecular forces in between those molecules. Well, once it gets melted, I can start heating up the liquid again. So my kinetic energy is starting to change again because I'm increasing my temperature, but my potential energy is staying the same. So potential energy deals with the intermolecular forces, and kinetic energy is about the temperature and the movement of the molecules. So right here, when I get to this point, I have another flat line. So that means it is a phase change, so I'm going to be boiling it at that substance, or at that temperature. So once I boil all of my liquid, I'm going to have a gas, and then I can start to increase the temperature again at that point. All right, so for the opposite, so if I start off at a high temperature and I go down to a low temperature, I'm basically doing the opposite of what's being done here. So I'm starting off with a gas, I'm cooling it down, I'm removing energy from it, and then at a certain point, when I get to the boiling point, which is the same as the condensation point, it just depends on what you're doing with the energy as to what it does. I'm going to go from a gas to a liquid, and then once I get all liquid, I can start cooling that liquid down, and then at this point, I'm just going to freeze the substance. So anytime that you have a flat line, that's a phase change. Kinetic energy is not changing at that point because all the energy, instead of going into increasing the temperature, will go into either creating or breaking intermolecular forces here. Okay, so in this particular diagram right here, energy is actually being removed from that substance. So anytime that I cool something down, I'm removing energy from it. And the reason that that's important is because delta H and Q would be negative in those cases. If I'm heating it up, delta H and Q will be positive. All right, so if we're doing math in this kind of situation, anytime that my temperature is increasing, I can use Q is equal to MCAT because my temperature is changing on these steep parts of the graph. While on the flat lines, I can't use that because temperature is not changing, and there is heat energy involved in it. So we can't say, well, delta T is 0, so Q is 0. That's not the case. Anytime that we have a phase change, what we can do is we can multiply the number of moles of that substance by the molar heat of fusion or the molar heat of vaporization. All right, so it's going to be an endothermic process when you boil, you melt something. You're adding energy. So delta H is going to be positive. So delta HQ will be positive in all those cases. Also, if you were to calculate delta H or Q at a phase change, you can take the number of moles and multiply it by delta H of vaporization or fusion. So vaporization is used when we boil or condense something. Fusion will be used when we melt or freeze something. So that's how you would get that there. And the reason that it's important to notice if they're gaining energy or losing it is because if you are losing the energy, this becomes negative. So if we're an exothermic process, so if it's being cooled down, I'm removing the energy from that substance, delta H will be negative. So delta H for vaporization and fusion will be negative. All right, so when we talk about bonds, atoms will bond at a distance which lowers potential energy. So basically you have things that are attracted to each other. So the nucleus is attracted to the electrons. However, you've also got repulsions in there because the two nuclei will actually start to repel each other. So when atoms bond, they bond at a distance that will maximize their attraction and minimize the repulsion. That distance is called the bond length. Well, the amount of energy that we have in between those two atoms, the amount of potential energy, is equal to the bond energy. Now, the more electrons you have involved, the stronger the bond. So basically, if you have a triple bond or a double bond, you have more electrons, those bonds will be stronger, but not necessarily 3 or 2 times. Now, something also to note is the distance. If you have a shorter bond, you have a stronger bond. And that's because of Coulomb's law. The distance between the charges would be less, which makes them more attracted, which makes the force of attraction greater. All right, so now if I want to calculate delta H with bond energy, you have to remember this. This is very important. Okay, when bonds are broken, energy has to be put into that process. So to pull atoms that are attracted to each other apart, you have to put energy into that process. And that's true with anything. If you're breaking up any kind of attraction between molecules, bonds, you have to put energy into that. Now, when bonds are formed, so you're bringing atoms together that are attracted to each other, energy will be released. So that means that delta H will be negative when you have a bond that's formed and positive when you have a bond that's broken. So if you're given bond energy, you have to draw the Lewis structures. Don't forget to account for the coefficients. So if you have 2 molecules of something, make sure you draw out all the molecules. Count your number of bonds. Then you're going to add the energy for the bonds formed and bonds broken. Because when you put bonds together, when you form them, that's an exothermic process. You're going to make that negative, and then basically just add the sums. This information is not given to you on the reference sheet, so that's why it's important to notice if bonds are being formed, it's an exothermic process. All right, so let's look at a problem. All right, so we have a reaction. We're given bond energy for 3 bonds. So the first thing we're going to do, we're going to draw out these Lewis structures. Okay, so 2 H2s. I have this. All right. And then I also have O2, which is this. Make sure you're drawing the Lewis structures correcly because they could give you the single bond between the 2 O's, and that would not be correct. All right, and then H2O would be this. All right, so now we're going to count our bonds. H2s. Okay, so I've got 2 of these, and my bond energy is equal to 436. So 2 times that would give me 872. All right, so O2, I just have 1 of those, and that would be 495. So 1 times that would just give me 495. All right, so now let's go to this side. For water, I have 4. I have 1 bond here, 2 bonds, 3 bonds, 4 bonds. 4 of these. And each one is 463. So multiply 4 by this. I get 1852. All right, so now let's add these 2 together because these are the bonds that are being broken. Okay, so this plus this would give me my bonds broken, which would be 1367. All right, well, this is my total for bonds formed, 1852. Well, remember, if you make bonds, that is negative. If you break bonds, that's positive. So now we just add them together. So this plus negative 1852, because we're making bonds, which means that is negative, would give me negative 485, and I would have whatever unit they included here. All right, so you can also calculate delta H with delta H of formation. So the delta H of formation was given here, and you were given a reaction. So you have to remember to account for the coefficients. This equation is given to you on the reference sheet, so you don't have to memorize this. So it's going to be products minus the sum of the reactants. So if you are given something in its standard state, it will be 0. And that's due to the fact that the element's formed from itself, so there's no change in energy when you do that. So aluminum, bromine, any of the diatomics, all of those, delta H of formation will be 0. All right, so what we're going to do, we're going to do the sum of the products and the sum of the reactants. So we have CH4, or actually let's do, because it's products minus reactants, let's do the products first. So let's do water. So water is, I've got 2 of those, and then it releases 286 joules when I form water. All right, so O2, or I'm sorry, CO2, I've just got 1 of those, so negative 394. So that would be my products minus my reactants. So CH4, I've got 1 of those times negative 75 plus my oxygen. Well, oxygen's not given because oxygen state, it's in its standard state, which means that its formation should be 0. All right, so now basically just multiply it out and add it together. So you get negative 891, and that's going to be kilojoules for this reaction. All right, so you could also calculate delta H with Hess's law. So if you're given a series of reactions and you're asked to get delta H of a reaction, you can basically combine these together and you can flip the equation, multiply, divide, whatever you need to do to get that equation that you want. Just remember to do the same thing to delta H. Then at the end, take your delta H's and add them together. All right, so the first one, let's look. This is the reaction I want. I've got P4, and this one has P4 in it, but it's on the wrong side. It's also got 1, so I'm probably just going to flip this one. So I should get 4PCl5 produces P4 plus 10Cl2. So that means I'm going to flip this. So this is no longer positive, it's negative. All right, so now let's look at the next one. Well, I've got PCl3 and PCl3, but I've got 4 of them. It's on the correct side, but I need to multiply this out by 4. So let's do that. So 4 PCl3 plus 4 Cl2s produces 4 PCl5s. So whatever I do to this, let's do that to delta H. So I'm multiplying that by 4. Okay, let's make sure that we get the equation we want. So I have 4 of these. Oh, this will cancel. And I will have some of these cancel. So this one will cancel because this one has the least amount. So I take away 4 from here. So I'm left with 6. So I do have the equation now. 4 PCl3s produces P4 plus 6 Cl2s. So basically at the end, just add your delta H's together. And that gives me 3,771. All right, so now sometimes you might not be given all of the reactions, so you actually have to write them out. So you might have to write out the heat of formation reaction or the heat of combustion reaction. And typically, if you get to the point where you think you might have to use Hess's law, but they don't give you the reactions, you're going to have to write it out. And the main thing to remember when you're writing out these heats of formation and heats of combustion is that you're only using 1 mole of whatever that substance is. So if I'm looking at heats of formation, when I write out an equation for heats of formation, I only can have 1 mole of that substance. So let's do that. All right, so this is heat of formation. So I'm making C2H6, and I can only have 1 mole of this. That is typically a gas, by the way. All right, so I'm making it from my elements. Well, what elements make this up? Carbon and hydrogen. So carbon would be made or used to make this. So its standard state is usually graphite. All right, plus hydrogen. Hydrogen is the other element that makes this up, so H2. Okay, so now let's balance it. But remember, when you balance it, you have to have only 1 mole of that thing. So I can only have 1 mole of C2H6 because if it gave me the heat of formation, well, the heat of formation is when you make 1 mole of that thing. So I need 2 carbons and then 3 of those. And this still only is 1 mole, so I don't have to worry about reducing it to a fraction. All right, so let's look at heats of combustion. So when I write a heat of combustion reaction, it's when I combust 1 mole of that substance with O2. So you're either going to be making an oxide or you're going to be combusting a hydrocarbon. If you combust a hydrocarbon, you're going to make CO2 and water. All right, so let's do magnesium. So I'm combusting magnesium with oxygen. Well, the only thing I can do with this is combine it. So magnesium has a +2 charge, oxygen has -2, so it should be MgO. Well, it's not balanced, so if I put a 2 here, that means I have to put a 2 here, but that breaks my rule because I can only have 1 mole of that substance. So basically, I need to get this down to 1, so I'm going to divide everything by 2. So 2 divided by 2, 1 divided by 2, and then 2 divided by 2. So that changes it to Mg plus 1/2 O2s produces this. So you can see coefficients of 1/2 like this in enthalpy problems, basically. And the reason we do this is because it's the energy to combust 1 mole of methane or magnesium, so only 1 mole. All right, so CH4. Well, if I combust that and O2, it's a hydrocarbon, so I'm going to make CO2 and water. All right, so let's balance. I need 2 more waters and then 2 of those. And this is okay because I still only have 1 mole of methane. Okay, the reason that this might be important is because you can be given a problem and you're given heats of combustion and maybe heats of formation, and you need to get an overall reaction. Well, if you're given a heat of combustion and heats of formation, you can write out these equations and use Hess's law to get a different reaction. All right, so when we talk about IMFs and heat energy, you have to remember that in between your molecules you have electrostatic forces, which attracts those molecules together. So it's going to require energy to pull those things apart. So you can heat it up to pull those things apart. The stronger the IMF, the more energy required to break that bond. So the higher the boiling point, melting point, surface tension, viscosity, and the lower the vapor pressure. So remember that you have LDF, that's the weakest intermolecular force. Then you have dipole-induced dipole, and I don't know how much I've talked about this, but dipole-induced dipole is where I have a nonpolar molecule and I happen to come into contact with something that does have a dipole. So what ends up happening is that positive end kind of pulls the electrons over there to make a temporary charge. Then after that I have dipole-dipole because those have permanent dipoles, so the positive and the negative end, and then hydrogen bonding. Okay, so remember, if a substance has more mass, then it has a higher London dispersion force. Don't refer to the mass, though. We say that it has more polarizable electrons. That's the College Board accepted answer. Mass, don't include the mass. Yes, you look at the mass. If it has a higher mass, then it has a higher LDF, but what you say is that it has more polarizable electrons. So more electrons that can be pulled to make those temporary dipoles. All right, so when we talk about Gibbs free energy, we're talking about entropy and we're talking about heat. So in chemistry, we like it hot and we like it chaotic. So delta H, if we have a reaction that releases energy, that's going to be considered to be a favorable thing. Okay, so if an delta H is negative and it's exothermic, we're going to say it's favorable. Now, with entropy, entropy is the measurement of disorder. So if your delta S increases, then you are becoming more disordered. If it decreases, then you're becoming more ordered. You're cleaning up. So favorable reactions are going to create more disorder. Well, how do you do that? Well, you can spread molecules out more. So go into a gas state. You can dissolve it into water. You can go into a reaction that makes more particles, more complicated particles. Okay, any of those things increase disorder. So basically, if you become more messy, you're becoming more disordered. So delta S will actually be positive when favorable. You have to remember that entropy is a measurement of disorder, not order. So delta H will be negative when it's favorable. Delta S will be positive when it's favorable. Now, delta G is spontaneity. Spontaneous reactions are going to be favorable and produce lots and lots of products. So G is going to be negative for spontaneous reactions and be positive for non-spontaneous reactions. Now, if it's at 0, the reaction's at equilibrium. All right, so if you're trying to determine delta G or delta S, you can do the same thing that we did with delta H. If you're given the delta G's of formations or the delta S of formations. So you can use that, or you can use Hess's law, same way that we did with delta H. All three of those things are related in this equation. So delta G is equal to delta S minus temperature times delta S. Okay. Use caution when you use this equation to actually solve for delta G, because entropy is actually measured in joules per Kelvin, and delta H is usually measured in kilojoules. So you have to convert to kilojoules first if you use this equation. Okay, so if you're trying to decide if a reaction is spontaneous, remember, we like it hot and we like it chaotic. So we like exothermic reactions and we like reactions that cause more disorder. So we like it when delta S is positive and delta H is negative. So let's go through all the scenarios. Okay, so if we have delta H and it's negative, that means it's exothermic, it's releasing heat. We like that. Now, if we have a positive delta S, that means there's more disorder. We like that. Okay, so we like when it's hot and there's more chaos. So we're happy in both those areas, so yes, we're definitely going to have a spontaneous reaction. Okay, so now let's look at an endothermic reaction. Well, we don't like that. We don't like having to put energy into things. We also don't like it when it becomes less disordered, when it becomes cleaner. So we're sad in both cases, so it's definitely non-spontaneous. It's a teardrop. All right, so now let's look at another situation. If we're releasing energy, so it's exothermic, that's good, we like that. But it became more clean, so we don't like that. So it's going to depend on the temperature. So if we think about this, an exothermic reaction is going to produce heat. So A plus B produces C, O, and then energy. We like that. We like it when it produces energy. So if we have an exothermic reaction and it's going to produce more products, well, it needs to be at a low temperature, because if we had it at a high temperature, the reaction is going to shift and go back to the reactant side, which is bad. So exothermic reactions are favorable at low temperatures. So the reaction will be negative or will be spontaneous at low temperatures. All right, so let's look at this one, endothermic. Well, we don't like that. We don't like having to put energy into things. Oh, but we do like when it becomes more chaotic. So again, it's going to depend on the temperature. So in an endothermic reaction, energy is a reactant. All right, so energy is a reactant here. So that means that if I add energy to it, I'm going to produce more and more products, which I like. So if we have an endothermic reaction, those are favorable at high temperatures. So my reaction will be spontaneous at high temperatures here. Okay, so a quick note. Questions will ask if a reaction is spontaneous or not, and then they might say in relation to this equation. So what they're looking for is a mathematical explanation, not my happy face, sad face explanation. So basically, they are asking, okay, so if you have a high temperature, what happens? Basically, you're going to talk about this equation, and you're going to say that when T is high or low, depending on what the situation is, then the magnitude of the temperature times, oh, this should be delta S, will be greater than or less than delta H, making G negative or positive. So basically, if delta G is supposed to be negative, then T times delta S has to be higher than delta H. If delta G is supposed to be positive, then this has to be smaller than delta H. All right, so just a few more notes. Thermodynamically favorable reactions might be slow. So yeah, they're spontaneous, but they might actually just occur very, very slowly. And that's because they have a large activation energy, but they're still spontaneous. So if a reaction is not spontaneous, then it can be forced by applying energy or putting reactions together that do produce energy. So if you have a reaction that shares a common intermediate, they can be put together if one releases energy and one requires it. All right, so G and big K are related too in this equation. So if K is larger than 1, delta G is going to be negative. So if I take the natural log of something that's greater than 1, that means that I'm going to get a positive number. And that means that delta G will end up being negative. So those are going to be spontaneous reactions, and it should make sense because if K is larger than 1, the reaction is product driven. It makes lots and lots of products. Well, those are spontaneous reactions. Now, if K is less than 1, then it's probably not going to be spontaneous.